These are the Physics Unit 6 Forces notes. On the board in class, the vocabulary words are mass, weight, inertia, forces, Newton, net force, gravitational force, FBD, and equilibrium. Otherwise, we will be talking about forces in general, Newton's first law, Newton's second law, mass versus weight, and Newton's third law. We will also be talking about universal gravitational force, which we'll have a big idea about that. We'll talk about a formula for universal gravitational force. We'll talk about how that applies to the how universal gravitational force follows the inverse square law. We'll do an example solving for gravity. We'll do an example solving for force, and we'll do an example solving for distance in these notes. All right, so a force. A force is any influence that can change the velocity of a body. Forces can act either through the physical contact of two objects, like a push or a pull, or at a distance, which is called like a field force. Those would be magnetic forces or gravitational forces. Contact forces are things like frictional force, tensional force, normal force, air resistance force, applied force, and spring forces. We will talk about all of these in this class. Action at a distance forces or field forces would be gravitational force, electric force, and magnetic force. We really only talk about gravitational force in this class. Electric force is covered just a little bit next semester, but magnetic force is primarily covered in upper level physics classes. So what do we mean by balanced and unbalanced forces? Forces on the book are balanced. The table pushes up on the book, gravity pulls down on the book. Since they have the same value, the book does not move up and down. But if I move the book to one side, then the forces on this book are unbalanced. So as the table pushes up on it, gravity pulls down on it, but friction pushes leftwards with 5 newtons worth of force. So now it is moving, so there is an unbalanced force. All right? So balanced forces are equal and opposite in direction. Now the net force, which is a vocabulary word, is the vector sum of the forces acting on an object. Remember, we've talked about vectors before, and vectors are just magnitude and direction. So if I talk about the net force on this first block, I have two 5 Newton forces going to the right. So that would mean that my net force was 10 newtons going to the right. On the next block, I have 5 newtons to the left, 5 newtons to the right. And so that would actually be 0 newtons as my net force, because those would be subtracted because they're going in opposite directions. Then for the next one, I have 5 newtons to the left, 10 newtons to the right. So since they're in opposite directions, we subtract the vectors to find the sum being 5 newtons right. Okay. If all the forces are balanced, we say that the object is in equilibrium. So equilibrium means that it's balanced. It doesn't mean that it's not moving, okay? It just means that it's balanced. So on my book picture, the table pushes up on the book has a weight pushing down. On this, I'm pushing down the spring is pushing up on my hand. On this, the little girl has tension in the ropes going up and her weight force going down. Those are balanced out. Now this one, she's applying 75 newtons worth of force to the right. There is 75 newtons worth of friction to the left. She is moving this box, but it's moving at a constant speed. So what you also need to understand is forces are balanced, and an object can be in equilibrium if it's either at rest or moving at a constant speed. Those are the two ways that it can be balanced, all right? So it means that it's not accelerating in any way. If it's accelerating in any way, okay, meaning it's changing directions or it's changing its speed, that's acceleration. then that would be an unbalanced force. But if it's keeping the same speed it's going, or it's at rest, then it's not accelerating, and that would mean that it is balanced forces or in equilibrium. So what are net forces? Again, they're a vector sum. And so I have 1,200 newtons going up and 800 going down. So the net force would be 400 newtons up. So I would subtract those two. Here I have 600 newtons going up. I have 800 newtons going down. So the net force when I subtract those two would be 200 newtons down. This one I have 50 up, 50 down, and 20 to the left. So my net force would be 20 newtons to the left. These are known as free body diagrams. Free body diagrams are a square picture where you actually show the vectors. So this is a vocabulary word, it's an FBD. So it shows the vectors of the forces on an object. Okay, so I will always put the base of the vector on the actual object with the arrow pointing whatever direction it should be. Okay, so Newton's first law. Newton's first law is also known as the law of inertia. And according to Newton, really the thought process is if no net force acts on it, a body at rest remains at rest, and a body in motion remains in motion, and at a constant speed and in a straight line. Most of y'all have just heard this as whatever an object is doing, it will keep doing, unless acted on by an outside force. Okay, so if there's an unbalanced force, then it will change. Otherwise, it's just going to keep doing exactly what it's doing. So if it's at rest, it's going to stay at rest. If it's in motion, it's going to stay at that constant speed and in a straight line. Because if it changes speed, that's acceleration. If it changes direction, that's acceleration. So then that means that it's not no net force anymore. There is a net force. So this is also known, like I said, as the law of inertia. So let's talk about what mass and inertia are, because inertia is one of your vocabulary words. So the property of a body to resist any change in its state of rest or its uniform motion. So if an object resists changing whatever it's doing, that's inertia. Most of y'all know the word inertia from Bill Nye the Science Guy's intro, because you'll say, what is inertia? Inertia is property of matter, because that's part of the intro for Bill Nye, and so y'all heard it for years and years and years when y'all watched that. But it's really just related to the amount of matter that's in an object. So the more mass an object has, the more inertia it has. All right? So mass and inertia are directly tied together, all right? And inertia is really just a resistance to change what an object's doing. Mass is always measured in kilograms as we go forward in this class. So if I wanted to measure inertia, I'd also measure it in kilograms. All right. This is also why we have, for example, the offensive and defensive line players. Typically, they're pretty big on a football team, and the reason for that is when the offensive line gets set, if they have a lot of mass, then their inertia to move them is a lot harder. Okay, so that becomes why we do things like that. Also, if you think about a VW Bug coming to a stop and an 18-wheeler coming to a stop, it's a lot harder to get that 18-wheeler to come to a stop because it has so much inertia. So to change its motion takes a lot more force. Okay. So motion tends to continue unchanged if there's no unbalanced forces. So an elephant at rest tends to remain at rest. Also, too little force in too little time to overcome the inertia of the tableware will allow you to pull the tablecloth out from underneath all of that tableware. So a lot of y'all have seen that trick before. All right, Newton's second law. Newton's second law is our, what I call, calculation law. All right, and Newton's second law says that the net force acting on a body equals the product of the mass and the acceleration of that body. The direction of the force is the same as the direction of the acceleration. That's always really important to remember, okay? So the net force will always be in the same direction as the acceleration. When we look at this in equation form, it really just means F equals ma. All right. Force is going to be our F. M is going to be your mass, and it will be in kilograms. And A is going to be your acceleration, and it will be in meters per second squared. Force is always going to be measured in something called a Newton. All right. And that's really just a combination of a kilogram meter per second squared. So the force of a hand accelerates the brick. Okay. Let's talk about a specialized form of force. Okay. Weight is the gravitational force with which the earth attracts a body. It's important for you to write this. Weight is actually a vocabulary word, but weight is a force. You need to write that really big on your notes. Okay? Weight is a vector value, and it is a force, and it's very different from mass. Mass is a scalar quantity. Okay? So the weight of a body does vary with its location near the earth, okay, or other astronomical bodies. Astronomical. Yeah, I'm not even saying that word right today. So it would differ from here to the moon, or here in Jupiter, and here in the sun. Any type of those other planets, our weight would change because of the fact that it is directly related to gravity, and gravity is specific to location. All right, whereas your mass should be the same everywhere. If I go from here to the moon, then I should have the same mass as I do here on Earth, unless I lose a body part or something along the way. Okay, so the weight of a body is again that force, and it's caused by the downward acceleration of gravity. So when we calculate it, we'll say weight is mass times gravity. So I call it F of G, so I call it a gravitational force. So that's how I list my weight force. But a lot of people just list it as a capital W. I'm not picky which way you use it, but later on we'll use a capital W for work, so I don't want to get it confused lots of times. But M is for mass and G is for gravity. We know in this class we use gravity as 10 meters per second squared. So you'll just take the mass in kilograms, multiply it by 10 meters per second squared, and you come up with the weight. Okay? Now, in the metric system, which is the SI system, the unit for force is a Newton. A Newton is actually just a kilogram meter per second squared. That's really just important to understand that it's a derived unit, because it allows us to write an N instead of having to write kilogram meter per second squared all the time. Okay? So if I have twice as much force, it'll produce twice as much acceleration on one single brick. If I have twice the force and twice the mass, it will make the same acceleration as when I just had one hand on one brick. If I have the same force and I have two bricks now, so if I just have one hand pushing on two bricks, it's going to be half as much acceleration. And if I have three bricks but only one hand of force, then it's going to be a third of the acceleration as when I just had one hand and one brick. So it's just really a ratio of the fact that you can figure things like that out depending on how much force is applied. That will affect the acceleration. All right. Newton's third law. Newton's third law is what I like to call the law of pairs. Okay, according to Newton's third law, when one body exerts a force on another body, the second body exerts on the first an equal force and in the opposite direction. Most of y'all know this as for every action force, there's an equal and opposite reaction force. Most of the time, though, you guys don't say the word force. You say for every action, there's an equal and opposite reaction. But really, the whole thought of that particular saying is that it is a force. So you have to have two objects, two forces, which will then be equal and opposite. Okay? The hammer pushes on the stake pushes up on the hammer. Two objects, two forces, equal and opposite. Okay, forces always occur in pairs because of this law. So the tire pushes on the road pushes on the tire. The rocket pushes on the gas pushes on the rocket. Okay? Now, net force also, we've talked about it as a vocabulary word. It's a vector sum of forces. It can also be designated as a summation. That's an epsilon F. Okay, epsilon means summation. So the second law is key to understanding the behavior of moving bodies, since it links cause, force, and affect acceleration in a definite way. Okay, so if I know the mass of this van, and I know its acceleration rate becomes a certain value, I can find how much force was applied by using my Newton's second law. All right. So let's do some problems, because these are going to be calculations you're going to have to do on your test. So these are example problems, and you can do these anywhere you want. This is not the examples that I broke it up into, but you can do them like on a separate sheet of paper and then have them included in your notes. So a force of 3,000 newtons is applied to a 1,500 kilogram car that's at rest. I want to know what its acceleration is. Well, I know the force value, and I know the mass, and I know Newton's second law. Okay, I also know that it's starting from rest, so F equals ma, and if that's the case, I can rearrange that formula to be A equals F divided by m. I can substitute in my variables that I know, do my calculation, and end up with 2 meters per second squared. I can then also ask you, what will its velocity be after 5 seconds? We have several formulas that we dealt with when we did kinematics that have acceleration in them, that have distances and velocities and times and things like that. So I have this formula that's Vf equals Vo plus At. I know the original velocity was 0. I know my acceleration value is now 2 meters per second squared, and I know a time of 5 seconds. So I can plug in my information, and I can find out that after 5 seconds, this car would be going 10 meters per second. Okay? My next example, I have a 1,000 kilogram car that goes from 10 to 20 meters per second in 5 seconds. What force is acting on it? Well, I have a mass, I have an original velocity, I have a final velocity, and I have a time. Okay, those would be all my variables. Well, I want to find force, and force is mass equals acceleration, but I don't have acceleration. I do have a formula, though, for acceleration, and that is Vf minus Vo over t, or the change in V over t. So I could find the acceleration, then multiply it by the mass, and actually solve this problem. So I could do my 20 minus 10 divided by 5, and then multiplied by 1,000. That would give me 2,000 newtons. So there would be a force of 2,000 newtons acting on this car. I have a 60-gram tennis ball. It's approaching a racket at 15 meters per second. It's in contact with that racket for 0.005 seconds, and then it rebounds at 20 meters per second. Find the average force exerted by the racket. Okay, so I have a mass. That mass was given to me in grams, so I have to convert it to kilograms. To do that, remember there are 1,000 grams in a kilogram. I know an original velocity of 15 meters per second. I also know a final velocity of 20 meters per second, but it's going in the opposite direction. So in order to designate that opposite direction, I have to go ahead and give that a different sign. So I would say that my 20 meters per second would be negative because it's going in the opposite direction. I also know my time value, which is 0.005 seconds. With that information, I can find the force because I can say F equals ma, and I know that A equals Vf minus Vo over t. So I could solve for that first, and then I could plug it in, or I could just substitute it all at once and have negative 20 minus 15 over 0.005, all multiplied by 0.06. And that would give me a negative 420 newtons. If I have the brakes of a 1,000 kilogram car and they exert 3,000 newtons worth of force, how long will it take the car to come to a stop from a velocity of 30 meters per second? Okay, a couple of things that I need to realize here. I have a mass, which is 1,000 kilograms. I have a force, which is 3,000 newtons. I have a car that wants to come to a stop, so I have a final velocity of 0. And I have an original velocity of 30 meters per second. The issue is I'm actually going from a speed to stop. So hopefully you would realize that that is what kind of acceleration? Hopefully you say negative acceleration. So if that's the case, I have to somehow get negative acceleration. So when I identify my variables, I'm going to identify my force as a negative value. Remember I said the acceleration and the force would always be in the same direction. So if I have negative acceleration, I have negative force. So I have my original velocity, I have my final velocity, and I'm looking for a time. In order to find that time, I'm actually going to have to find my acceleration first. So I'm going to do my negative 3,000 divided by 1,000, which is going to give me a negative 3 meters per second squared. I'm then going to use my formula manipulated to solve for time of VF minus VO over A. I'll substitute in what I know, and I'll solve for 10 seconds. Now I could say how far will the car travel during this time as well, so while it's decelerating. So I could go back to the formula of D equals VOT plus 1/2 AT squared. That's also from our formula chart. So I know my original velocity was 30. I know my time is 10 seconds now. I know my acceleration value is a negative 3 meters per second squared, and again, I know my time is 10 seconds. So I can plug in all that information, not forget my squared, and don't lose my negative sign, and I would get an answer of 150 meters. If I have a net horizontal force of 4,000 newtons and it's applied to a car at rest whose weight is 10,000 newtons, what will the car's speed be after 8 seconds? Okay, well, a few things that we need to realize. I have a weight and an applied force. I have an applied force of 4,000 newtons and I have a weight force of 10,000 newtons. I then have a time of 8 seconds, and I know that my car started at 0. If you remember, to solve for weight, it is mass times gravity. So if I wanted to find the mass of this vehicle, I could say F divided by G. Okay, so that's going to be my 10,000 newtons divided by 10, because we know gravity for our class is 10 meters per second squared. So the mass of this vehicle is 1,000 kilograms. The reason that's important is because I'm going to have to come up with an acceleration value. And to come up with acceleration, I have to do my applied force divided by my mass. But if I didn't know my mass, I wasn't going to be able to find that. So I'm going to do 4,000 divided by 1,000, which would then give me 4 meters per second squared. Now I can use my kinematics equation of VF equals VO plus AT, and I can solve by saying 4 times 8 seconds, which would give me 32 meters per second. So we are using quite a few formulas and different manipulations, and you kind of have to pay attention to that, but those are all formulas that we've seen before. All right, I'm going to end this one, and I will start part 2 of these notes, and you can go from there.